Recording. So thank you, everyone. Welcome to our second session of the annual meeting of the Topological Data Analysis Center. And it's my great pleasure to introduce Professor Michael Farber from the Queen Mary University of London, who will talk about topology and automated decision making. Over to you, Michael, please.
Thank you. Thank you very much, Vitaly, and thanks to all organizers for inviting me. It's a pleasure to speak at this annual event of the Center for Topological Data Analysis. Okay, so my title is Topology and Automated Decision Making. And I will start from a very general kind of view of what is decision making. It's a very important part of our life. In our life, we make several important decisions which determine all our future. But in terms of decisions for the society or decisions for companies or other decisions, I mean, they are all important decisions. And what I will discuss in this talk is decisions when the choice which we are supposed to make lies in an infinite space, like infinite topological space. So decisions can be like buy or sell, kind of discrete decisions, left or right, discrete decision. But decisions which will be relevant for this talk are more complicated decisions when you choose from a continuum of possibilities. So there is a well-known Turing test, which tests what is intelligence, what is artificial intelligence or human intelligence. And I mean, it was a big breakthrough when Turing suggested that it is not necessarily something physiological or biological. It can be anything which answers questions, which gives answers which you cannot distinguish from answers given by human. So this is a picture from this well-known movie, which is called The Imitation Game. And this is a picture of a robot moving on the plane, and there are some obstacles. So this picture will be quite relevant to my talk. So the robot has initial position and the final position, and its goal is to choose the trajectory, the path from the initial to final position. And here there is a continuum of different choices. So this question appears in self-driving cars, GPS, and it boils down to what is called motion planning algorithm. So this algorithm, which I will discuss in my talk, has as input the initial and final state of the system, and as output, it produces a trajectory from the initial to final state, avoiding obstacles. Before I start my main topic, I want to mention another area where these decisions are taken out of continuum possibilities. And this is area which is called social choice theory. It's quite well-developed subject. It's, I should say, Kenneth Arrow in 50s wrote important articles in this field, and he got Nobel Prize for this. So there's some other important papers mentioned on my slide. So in this case, we have some space X of alternatives, and we have many voters, many people, participants, voters, and so each voter has certain preference which is a point in the space X. And I mean, our goal is to construct this function f, which is mechanism of aggregation of different individual choices, individual preferences, and to select one choice for the whole society. There are some natural conditions on this function. For example, unanimity means that if everybody wants X, some certain preference X, then this should be selected. And second condition is that if we, so this function doesn't depend on permutation of variables, it's called anonymity. So it only depends on the choices, set of choices by people, but not on individual choices. So I just wanted to mention this theory very, very briefly, and I will start with my main topic, which is motion planning algorithms and their complexity. So this part one will be kind of very general basic introduction, and part two will describe more recent results. So, okay, so I'll start with part one, mathematical formulation of the motion planning algorithm, motion planning problem. So we have a system. The system determines a configuration space. So each state of the system can be characterized by certain set of parameters, numerical parameters. So it can be viewed as a point in some Euclidean space, where dimension is the number of these parameters. And the variety of all these points in Rn forms a topological space, which we can consider as a configuration space of our system. So once we view our configuration space, we can forget about the system itself and think about the space and points being states. So in this example, we have robot arm, which has, let's say, 4 valves. Each can rotate independently. So in the planar case, the configuration space is torus of dimension 4. And if it is in R3, then the configuration space is a product of 4 two-dimensional spheres. So motions of the system are continuous curves in this space. The motion planning algorithm, so I see that some letters moved here. So the motion planning algorithm is a map A from pairs of states to continuous motions in our configuration space. This map must be such that if I apply this map and then I apply the standard map, which is called P, which somehow it moved away. This P, this standard map, is a map which associates with every pass the initial and final points. So the total composition should be identity, which means that we associate with every pair a pass which starts at the first point and ends at the second point. So in other, we note that this is a fibration in the sense of serve, and A is a section. So question, can we expect that this section is continuous? And continuity would be important because it would mean that if I make small perturbation of the initial and final configurations, then the trajectories which are suggested by this algorithm are close to each other, not unlike in this picture. So the answer is that it's not possible in general. A continuous section exists if and only if X is contractible. And an example, of course, is if we have a convex set in Euclidean space, then from every A to every B, we can just go along a straight line, and this will be a perfectly continuous motion planning algorithm. And this existence of this is because this space is contractible. Okay, so as a corollary, we can say that kind of negation of the previous statement, that if the configuration space of our system is not contractible, then any motion planning algorithm has instabilities. So it has these situations when small perturbations lead to big changes in the motion. And this instabilities, this level of or degree of instabilities can be measured numerically. And this measure is called topological complexity, which is described on this slide. So a motion planning algorithm A is tame if X cross X admits a partition into finitely many n+1 in this case disjoint sets, such that on each of them the algorithm is continuous, and on top of that each of the sets is an Euclidean neighborhood retract. So using this definition, we can define what is the topological complexity of a space. So this will be important for my talk. So topological complexity of a space is defined as a minimal integer such that X admits a motion planning algorithm with n+1 sets. So we fix X and we look at all possible algorithms, and minimal number of sets is exactly this TC of X, topological complexity of X. So this TC of X has nice properties. The first is that it depends only on the homotopy type of X, and it is zero if and only if X is contractible. So the first example is a circle which is not contractible, so TC is not zero, but it is one. So here we have two sets, F0 and F1. So F0 consists of pairs of points which are not antipodal, and F1 consists of points which are antipodal. So if they are not antipodal, we just make a motion along the shortest geodesic arc, and it will be continuous restricted onto F0. And if we are in F1, then we just choose an orientation on the circle and move A towards B in the positive direction to 180 degrees. So this shows that we can achieve two sets. So TC is less or equal than 1 in this case, but it cannot be 0 because, as we know, the circle is not contractible, so it is 1. And more generally, TC of spheres is 1 for n odd, and it is 2 for n even. So I will not discuss this. I'll just go further. So, I mean, it is important to have tools to give lower bounds for TC. And so, usually computation of TC consists of combining some lower bounds with upper bounds. And in good situations, they match, and we have an exact answer. So these lower bounds are based on cohomology. And this is, I'm just mentioning this on this slide. So we fix some field F, and we look at cup product in cohomology with coefficients in F. And we look at tensors in the tensor product of cohomology algebra to itself. We look at tensors such that if I apply this cup product, it goes to 0. So such tensors are called zero divisors. So examples are here. So 1 tensor u minus u tensor 1, or this is more general situation like this. So all these are zero divisors, and they're important for this question because of the theorem, which says that if there exist k zero divisors such that their product is non-zero, then TC is at least k. So this is our lower bounds, basic result about lower bounds. And upper bound is twice dimension. So this is together with the fact that the TC is homotopy invariant. So it's homotopy invariant, it's not exceeding twice dimension. So this is kind of basic upper bound. Of course, there are better upper bounds if we know more about X, for example, if it is connected to certain level. So for example, for surfaces, for orientable surfaces, TC equals 2 for genus 0 and 1, and then it becomes twice dimension when genus is 2 and higher. And this is actually typical situation that in most examples, TC will be twice dimension, but it's not always the case. I'll just probably skip this slide. I'll just go mention this real projective spaces. For real projective spaces, TC is immersion dimension. TC equals immersion dimension. So it equals the smallest k such that this real projective space can be immersed into RK. But for exceptional values of n, which are 1, 3, 7, for those values, TC equals m. So this result shows that in general, you cannot expect very simple recipe for computing TC, and that TC is linked to some deep geometrical problems of which are well known in topology. So here is a table of values of TCRPN for n up to 10. And you see, for example, here 137. So it will be 137. But also simple answer we know for powers of 2, 2, 4, 8, it is 2n minus 1. So for powers of 2 is 2n minus 1, but otherwise, I mean, there are some special series of numbers for which the answer is known, but in general, there is no general formula. These are references. So in particular, the last theorem is in this paper with Tabachnikov and Luzvinsky, and maybe just very briefly, I will mention some different development of this theory when we are in directed topological spaces. So spaces where there is some extra structure, where there is positivity of paths and not every motion is allowed. And this was developed in a recent article with Eric Goubot and Sagner, and it is applicable to control systems and concurrency theory. I just don't want to stay to go further on this. I want to, as Vitaly will appreciate, I will try to be on time. So I'll start my second part of my talk. which is parametrized motion planning. So this is more recent result and more recent development, and it is based on joint work with Daniel Cohen and Weinberger. So we want our algorithms to be universal, which means that they should be able to work under a variety of external conditions. So not in the specific case. For example, in the case of obstacles, we want our algorithm to work in a situation when the position of the obstacles are not known in advance, and our algorithm will work for arbitrary situations with obstacles. So, for example, in this slide, I actually want to describe a very specific situation when some military commander, well, kind of, it's not real situation, but I mean, it sounds real. So if military commander needs to control N submarines, and there are some mines in these waters, and these mines are moving every time, I mean, every 24 hours, the other side may move this mines. So positions of mines are not fixed. So this algorithm should be able to work under any position of mines. So in fact, positions of mines are an input of the algorithm. So the algorithm should start with knowing the current position of all submarines, desired positions of all submarines, and current positions of the mines. So this is what we call parametrized motion planning. So parametrized, so we can translate this situation into mathematical language as follows. So we can have a vibration from E to B. Base, our base represents external conditions. So for each point of the base, B, in B, we have the fiber, and the fiber is our configuration space under the given external conditions. So the input of the algorithm is a pair of states, E prime, lying in the same fiber. So it means that they live in the same external conditions, under the same external conditions. And our aim or output of this algorithm is a path gamma in E, which starts at E and ends at E prime, and lies all the time inside this fiber, given fiber. So it means that the external conditions are fixed, and we are implementing motion respecting these external conditions. Okay, so I'll just want to introduce some notations here. By EIB, we denote the space of continuous path gamma. Is there a question? You want to ask a question?
Yes. Could you go back one slide, Michael? Your condition seems to be, I just want to understand, make sure I understand it correctly. You seem to be saying that if you have 2 points in the fiber, you want to look for a path connecting the two points, all within the fiber. So given the problem, wouldn't you just want to restrict yourself to the case where the base is just a point, really?
Well, No, because I mean, the point of the fiber represents external conditions. So if I restrict the base to a single point, then it means that external conditions are fixed, and my algorithm will work only for that choice of external conditions. But if I don't do that, it means that my algorithm will be applicable will be universal. So it will work for every possibility, and it will be very clear in my example later.
Okay, so but that is what you're looking at. Basically, given 2 points, you want to find a path within that fiber.
Yes, exactly.
Okay.
Yes. So this notation is for paths gamma lying in a single fiber. And so this notation is pairs of points of E lying in the same fiber. So it is product of two, I think it's called Wheaton sum, I don't know. Anyway, so it's clear what it means. So we have this map projection pi, which takes gamma into initial and end points. And they lie in the same fiber because gamma lies in the same fiber. So we define, now this is the main definition, we define this topological complexity of this parametrized situation as a Schwarz genus of this vibration. So it means that, I'll just explain, it means that it is the smallest integer m such that the space of pairs lying in a single fiber, each time in a single fiber, but this fiber is not fixed. The space admits an open cover with the properties that over each of these sets UI, there exists a continuous section of that vibration. And this is an example which is the kind of most convincing, I hope. And it is actually example of all the submarines and obstacles. So suppose we have n objects, Z1, Zn, pairwise distinct in Rd, and suppose we have m obstacles, O1, On in Rd, which are also pairwise distinct. So in this case, the base will be configuration space of m distinct points. So a point in this configuration space B will be the configuration of obstacles. And the total space will be the configuration space of n plus m points, consisting of n objects and m obstacles. And the projection will take the whole configuration of n plus m points, and we forget about this Z1, Zn, and we look at only at obstacles. So this will be our projection. And in this case, this vibration is well known, and it's called Fadel-Norwood vibration. So in this case, so this is our B. And if I have two configurations lying in the same fiber, it means that they are, okay, maybe it will be clear on the next slide. Let's just go. I just want to go on time. Let's see. Yes, so this is, so let's see what it means actually exactly. So suppose I have two configurations. So they lie in the same fibers, and that means that positions of obstacles are the same, but they are different, well, different z's, Z1 and here Z1 prime and so on. So we want an algorithm to generate a motion, continuous motion of Z1, Zn, T, such that the initial is Zi, the final is Zi prime, and such that there is no collisions between the objects and between objects and the obstacles. Okay. So this is a question. Is it all right? Okay. So so now I'm just going to general situations. So a few examples of this TC, of this parametrized TC. So first, if our vibration is trivial vibration, it's a product, then this is just the usual TC. There's no change. It's not surprising. The second example is a little bit surprising. So here, if P is a principal bundle with a topological group with G which is connected, then TC of the parameterized TC is the same as the usual TC of the fiber, which is TC of G, and it is the same as the category of G. So this may sound a little bit discouraging, because it shows that in all these examples, this parameterized TC equals the usual TC. And actually, usually the first thing you try with vibrations, you look at Hopf bundle, which is actually a principal bundle. So in this case, this parameterized TC will be the usual TC of the fiber. So again, here we don't gain anything. So you don't get extra complexity from the base. However, our main result is this theorem about this parameterized topological complexity of the Fadel-Norwood vibration, which I described earlier. And the statement is that its complexity equals 2m plus m minus 1. So we see that here it depends on m. M is the number of obstacles. So it is it shows that it can be bigger than the usual TC of the fiber. I'll just show it on my next slide. Before I go to the next slide, I just want to say that here, yeah. Okay, let's just go to the next. So here's the fiber is the configuration space. Do you want to ask something?
I think you're about to answer my question, namely, what is the complexity of the fiber?
Oh, yeah, okay. Yeah, so this is a quick answer to your question. So the fiber is configuration space of n points in the complement of m fixed. Now they're fixed points in RD. And in this case, we know that TC is 2n. And actually, what was surprising when we computed this, it doesn't depend on m. So it doesn't depend how many obstacles, fixed obstacles, they don't add to topological complexity. But here, we see that these obstacles, is extra summoned m. So,
sorry, Michael, do you need some condition? Oh, D
yes, D must
greater
be,
than 3. But what about your previous result? Yeah,
it must be odd. D must be odd. For even D in even dimension, the answer is different, and it's in a separate, one less. For even D, it's different answer. But also here, it is assumed D is odd. For even D, it will be slightly a different answer, less by 1. So we see that if we take sorry. So if we take I just put this, sorry, this is not the right place. So in the case when we have one robot and 2 obstacles, so n equals 1 and m equals 2, so that this parameterized TC will be equals 3. and the usual TC will be equal to, and we see that in this case it is higher, but it can be higher by any number. Just want to come back to this and to say that the proof of this consists of a combination of upper and lower bounds, and they match to give the precise answer. So this lower bound is based on this theorem. Okay, so if we have this vibration, we have this delta, which is this diagonal map, and we look at induced map on cohomology by this delta. So, and we look at the kernel. So this kernel, we take the couplings of the kernel, and this parametrized TC is greater than or equal to the couplings of the kernel. So this is the theorem which we use for low bound. And in particular, if we consider, I don't want to go in the general case, it's too technical, but I want to illustrate the simplest case when we have one robot and two obstacles in 3 space. Then this configuration space has 3 two-dimensional generators, which each describes communication between the robot and obstacle, the robot and second obstacle, and between the 2 obstacles. And they satisfy well-known relations. So now if we take our space, which is this one, so we have Whitney sum of E with itself, and then it has generators, 5 two-dimensional generators. These are previous generators, and these are new generators, but there is no new omega 2,3 prime because it is the same. And here relations, and the delta acts on omega ij the same as omega ij prime. So we can check, one can check that this product of 3 zero divisors is non-zero. 3 elements in the kernel, their product is non-zero, which implies that TC, this parametrized TC, is greater or equal than 3. So this is our paper, which contains the full statement and proof. And we have also an explicit motion planning algorithm of this complexity, which is optimal. So just to finish, I want to say a few general words. So, I mean, what I discussed in my talk were kind of topological complexity. But once you want to design a specific algorithm, you will see that there are different arguments come in. Not everything topological can be realized geometrically. So there are restrictions on how this can be practically realized, and there should be different measures of complexity, which may be geometric or combinatorial, and we are thinking in this direction. But what we can see is that this combinatorial complexity for n robots with m obstacles, I mean, this complexity which we can see, sorry, there's bracket missing there, is about this number, which is quite big, number. Even for the case of 5 robots and 3 obstacles, this number is already 270 million. I know that many people saw this performance of drones in the sky, with, for example, in Tokyo Olympics, where many drones, thousands, were flying together. So this, this is a situation which is a challenge for topologists. It's a big complexity there. So I just want to finish by this statement, which was made 50-something years ago by Russian writer Alexander Solzhenitsyn. He said, "Topology, the stratosphere of human thought. In the 24th century, it might just possibly be of use to somebody, but for the present." So we see that 50 years ago, topology was understood, or was kind of had an image of a remote abstract mathematics, but this conference, it feels like a very important part of everyday tool of mathematicians. Thank you.
Thank you very much, Michael. Let's thank Michael for his talk. Yeah, I'll